In this lesson, we will introduce some important subgroups of an arbitrary group G called the center of G and the centralizer of a subset of G. So let's begin by talking about the center of a group. Let's give the definition. The center of a group G, denoted by capital Z of G, this is the set of elements in G that commute with every other element in G. So in symbols, the center of G equals the set of all elements G in group G, such that Gx equals Xg for all X in G. For a quick example, consider an abelian group G. So if G is abelian, then all the elements of G commute, so therefore the center of G would equal all of G. So it is a theorem that the center of G actually forms a subgroup of the set G. So to prove that the center is a subgroup of G, we're going to use the definition of a subgroup. Clearly, the identity element commutes with any element of G. So since the identity is in the center of G, we see that the center of G is non-empty. Now let G and H be in the center of G. We want to show that the center is closed under multiplication. Well, given any element X in G, GH times X is, by the associative property, equal to G times the product HX. And since H is in the center of G, H commutes with X, so this equals G times the product XH. Again, by the associativity of G, we see that this equals the product GX times H. And since little g is in the center of G, we can commute G with X, so this equals XG times H, and therefore GH times X equals X times the product GH. So we've just shown that GH times X equals X times GH. So we see that GH commutes with any element of X. So GH is in the center of G. Now we need to show that the center is closed under taking inverses. Now let G be an element of the center of G. We want to show that G inverse is in the center of G as well. Since G is in the center of G, then for all X and G, we know that Gx equals Xg. But then taking this equation Gx equal to Xg, and first let's multiply both sides of this equation on the left by G inverse, and then we'll multiply on the right by G inverse and simplify. So we start off with Gx equal to Xg, and multiply both sides on the left by G inverse. We get G inverse times Gx equals G inverse Xg. And then simplifying, this becomes X equals G inverse Xg. Now again, multiplying this equation by G inverse on the right, we get Xg inverse equals G inverse Xg G inverse. And again, simplifying, we see that Xg inverse equals G inverse X. But this last equation shows that G inverse commutes with any element X and G. Thus, G inverse is in the center of G. So we see that the center of G contains the identity, it is closed under multiplication, and it's closed under inverses. Therefore, the center of G is a subgroup of G. Now let's look at an example of a center of a group. So for n greater than or equal to 3, consider the dihedral group of order 2n. So let's look at the center of the dihedral group of order 2n. So recall the dihedral group consists of all the symmetries of a regular n-gon, and we can identify the elements of this dihedral group by n rotation, so the identity r squared all the way up to r to the n minus 1, and then the reflection s and the product sr squared up to sr to the n minus 1. So these are all the 2n elements of this dihedral group. Now we know that the center of D2n is a subgroup of D2n, and so therefore it contains the identity element. The identity commutes with every other element of D2n. So clearly the identity is in the center. Now consider just the rotations. every rotation is a power of the rotation r. So when we combine rotations, we're just combining powers of r. So we see that all rotations commute with all other rotations. So since all rotations can be simply written as powers of r, we see that all rotations commute with each other. So we see that rotations commute with rotations. But which rotations commute with the reflection S? So in order for a rotation to be in the center, it has to commute with all elements of D2n, so it's in particular got to commute with the element S. Well, we know the relation r to the power I s is equal to s r to the minus I, for I between 0 and n. So we see that the rotation Ri commutes with S if and only if S Ri equals RIS, but that equals SR to the minus I. So if we cancel S, we see that this is true. Exactly when Ri is equal to R to the minus I. But that's the same as the inverse of Ri. So we see that a rotation will commute with all elements of D2n if that rotation is its own inverse. So that is if Ri is equal to the inverse of Ri. But the only rotations that are their own inverses are R0, which is the identity rotation, and in the particular case when the polygon has an even number of vertices. So when n is an even number, then the rotation that rotates halfway would be its own inverse. So let's call this r to the power k when n is an even integer 2k. So if n is odd, the only rotation that is its own inverse would be the identity r to the power 0. So thus, we can conclude that the center of D2n is the trivial subgroup containing the identity if n is odd, and the center of D2n will equal the identity and the rotation RK that rotates the polygon halfway around 180 degrees. And this works only if n is even. So if n equals 2k, then the rotation r to the power k will commute with every other element of D2n. So for example, the center of D8, so this would be the symmetries of a square, so that would equal the set of the identity and the rotation r squared, which rotates the square 180 degrees, since 2n equals 8, which is 2 times 4, so n is 4, which is 2 times 2. So therefore, r to the power 2 is in the center of D8. Next, we're going to look at another example of a subgroup in G called the Centralizer. So we saw that an element of the center of G would be an element that commutes with every element of G. So given an element A in G, A might not commute with every single element of G, but we're guaranteed that A will commute with at least some elements of G. So for example, if you look at all the powers of A, the element A would commute with all the powers of A. So this leads to the following definition of a centralizer of a set A. You can think of the centralizer of a set A in G to be the elements of G that commute with all elements of A. So let's be precise about our definition. Suppose you have a non-empty subset of G. So let A be a non-empty subset of G. Then the centralizer of A in G denoted by C sub G of A is defined by is a set of elements G in group G such that G, A, G inverse equals A for all A in set A. So by multiplying both sides of this equation on the right by the element G, we see that alternatively the centralizer of A and G can be defined as the set of G in group G such that GA equals AG for all A in A. So from the second set, we see that the centralizer of A in G consists of all the elements in G which commute with every element of A. So the centralizer of A and G is the set of all elements of G which commute with every element of A. So now let's give some facts about the centralizer. First, the centralizer of A and G is actually a subgroup of G. Secondly, if G is abelian, then every element of G commutes with every element of A. So therefore, the centralizer of A and G would equal all of G. Third fact, for any group G, we can recognize the center of G to be the set of all elements that commute with G. So therefore, we could write this as the centralizer of G in G. Now let's look at an example of a centralizer. So consider the set of symmetries of a square, D8, which consists of the elements 1, r, r squared, r cubed, s, sr, sr squared, and sr cubed. So let's let A be the subgroup of D8 consisting of just the rotations. So 1, r, r squared, r cubed. Let's look at the centralizer of A in D8. Well, we've already discussed the fact that all the rotations commute with each other in D8. So in particular, all the rotations would commute with A. So again, since all rotations commute with rotations, we see that A must be a subset of the centralizer of A. And I'm going to write the fact that A is a subgroup of the centralizer of A, because A is a group itself. Now notice that S does not commute with every rotation. So since SR does not equal RS, which happens to equal SR cubed, we see that S is not in the centralizer of A. Then no element of D8 involving the reflection S could be in the centralizer of A either. So that means that SR, SR squared, and SR cubed are also not in the centralizer of A. Because if any of these elements were in the centralizer, then by multiplying by the inverse of the rotation, we would also have S in the centralizer. So the only 4 elements of D8 that can be in the centralizer of A are the rotations. So therefore, we see that the centralizer of A in D8 actually equals A.